In lecture 29 of our series on numerical methods in civil engineering, we will continue with our discussion on differential operators. The difference operators we have considered thus far include the shift operator, the forward difference operator, the central difference operator, the average difference operator, and the backward difference operator, and we have seen that they can be operated on using the rules of algebra and calculus to find appropriate approximation formulas. In the last lecture, we dealt with operator calculus, and during that we showed relations between various operators and various operators. For instance, between the difference operator, the forward difference operator, and the differential operator, and we showed that they are related through the exponential function. So, e to the power h d is equal to 1 plus delta, where d is the differential operator and delta is the forward difference operator. Using this, we also showed that h d is given by this relation in terms of delta. We also obtained a relation between the difference operator in this case the central difference operator, and the differential operator, and we showed that relation is something like this. By squaring this last relation twice, we can get a relation between d square, that is the differential operator applied twice, and various powers of the central difference operator, right. However, sometimes if you want to apply this relation directly, it creates problems. Well, why is that? Well, let us recall that the central difference operator is given in terms of function values at the mid step, right, at the mid step. For instance, delta f is equal to half of f of x plus h by 2 plus minus f of x minus h by 2. So, we need the function values at the middle of the step at x plus h by 2 and x minus h by 2. If we do not have function values at those steps, at the mid steps, then it is hard to use the central difference operator, right. Evaluating the derivative in terms of delta, therefore, derivative d in terms of delta requires us to know the function values at midpoints of the intervals. If the function values at the midpoints of the intervals are not known, that adds to the complexity, meaning the cost, right. We have to evaluate the function. So, it is always better if we can get the difference operators in terms of function values at the grid points at x plus h, x plus 2h, x minus h, and so on and so forth. How do we avoid this problem? To avoid this problem, we note that mu del f x, that is, if we apply the central difference operator first on a function and then we apply the average operator mu, then what do we have? So, if we apply delta on f, we get f of x plus h by 2 minus f of x h minus 2. On top of that, if we apply mu, then what do we get? Half of f, so mu of f of x plus h by 2 is equal to half of f of x plus h plus f of x minus half of f of x plus f of x minus h, right. So, mu operating on f of x minus h by 2 is equal to f of x plus f of x minus h, right. It is the average difference operator, right. So, x minus h by 2, it goes one half step back and it goes half step forward and adds them together and takes the half of that, right. So, that is my average, the averaging operator, that operating on this part gives me this part, that operating on this part gives me that. So, again it goes a half step forward, half step back and adds it together, right. So, that is given by that, right. So, and then if we add these two together, we get half of f of x plus h minus f of x minus h. So, what do we see? If instead of directly applying the central difference operator, if we apply the central difference operator first and then use the averaging operator, right, then we can get it in terms of the grid point values, right, f of x plus h and f of x minus h. Similarly, we can show that mu delta cube, that is mu operating on delta operated 3 times, or mu delta to the power 5, mu operating on delta after it has been operated 5 times can also be shown to involve function values evaluated at step intervals only. By step intervals I mean grid points, right, at grid points only. Thus, if we can get an expression for HD instead of mu delta and mu delta or mu delta cube mu delta 5 instead of delta cube delta 5 and delta, then the issue would be resolved, right. We would be able to evaluate the functions at the grid points. This can be done in the following manner. Let us recall that mu of f of x is equal to half x plus half h plus half x minus half h, right. That is, we just talked about that just a little while ago. Then using E is equal to h d, we have f of x plus half h, right. I can write this as h d by 2, right. We can think of it as this shift operator x plus half h. I can think of that as the shift operator operating over half a step, right. So, E f of x plus half h is equal to E operating on f for half a step, and I know there is a relation between E and the difference operator that involves the exponential. So, I can write this as half of E h to the power d by 2, right. F of x plus h is equal to E to the power h d. So, f of x plus h by 2 I am writing as E to the power h d by 2, right. Similarly, I am writing f of x minus half h as E to the power minus h d by 2, right. So, I write this like that, and that we recognize is the cos hyperbolic of h d by 2, right. It is the cos hyperbolic of h d by 2 operating on f of x. And again we said at the beginning of our discussion on operator calculus that we will say that two operators are the same if their action on any arbitrary function is the same. So, in this case f is an arbitrary function. So, we can write mu is equal to cos of hyper h d by 2, right. Now, we already saw in the last class that delta by 2 is equal to sin h d by 2. If you look back, we discussed that, right. So, since delta by 2 is equal to sin h by 2, mu is equal to cos h by 2. So, I can write cos hyperbolic square, and I know that cos hyperbolic square anything minus, now what is that? That is sine, right? There is sine there, right? So, cos, I am sorry, so that is a typo, right? So, that is actually cos hyperbolic square beta minus sine hyperbolic square beta is equal to 1, which we know that is an identity. So, from that we get mu square minus delta square by 4 is equal to 1, right. Mu square minus delta square by 4 is equal to 1, from which I get mu square is equal to 1 plus delta square by 4. Therefore, I can write mu 1 plus delta square by 4 to the power minus half is equal to 1, right. So, I just take the square root of both sides, right, and then bring it to this side and I get 1. So, if I expand this in this series, right, expand this series, right, by on the left hand side, then I get this expression. So, mu 1 minus delta square by 8 plus 3 delta 4 by binomial, right, binomial expansion. So, I get that is equal to 1, right, and then so this is equal to 1. So, now let me go back to my expansion right here, which was this. So, now I am going to multiply this right hand side with 1. So, I will get the same thing, right. So, if I multiply this by 1, or that is equivalent to multiplying it by this whole thing, right, because this whole thing is equal to 1. So, I can get h d is equal to mu times that times this, right, that was already there, right, that was already there. So, I get this, I get that, right, I get this, I might have a factor of 2 missing, I am not so sure, let us check. So, that is mu 1 minus delta square by 8 times that times delta minus delta cube by 24. So, I have a factor of 2 missing, right. So, but then I have adjusted that, right. So, here it is just h d by 2, right. So, that gives me mu d minus mu delta cube square plus mu delta 5 by 5, right. So, that involves terms like mu delta cube, mu delta to the power 5, which I know can be written in terms of grid point values, right, which I know can be written in terms of grid point values. So, I get an expression for the differential operator in terms of mu delta, which involves evaluating the function only at the grid point values. Okay. So, that is enough about one dimensional differential operators and one dimensional difference operators and the relation between them. Basically, the relation between differential operators and difference operators, how we can write the differential operator in terms of various difference operators, and most importantly recognizing what is the error, right, what is the order of the error when we write those difference operators in terms of the differential operator. Recall that we found that for the forward difference operator our error is linear, right, we have a linear error. But when we write the differential operator in terms of the forward difference operator, we have a linear error term, right, the error is of order h, while when we wrote the central difference operator, when we wrote the differential operator in terms of the central difference operator and we expanded it in series, we found that the error was of second order, right, it was the error, the leading term in the error was of h square, was of order h square. So, that is very important to recognize that when we use different difference operators, we can use different difference operators to approximate our differential operators and we can get different orders of error. Well, until now we have considered differential as well as difference operators in one dimension and have attempted to establish relations between them. However, we looked, before we started looking at difference operators, we looked at partial differential equations, right, and we saw that most physical problems, like they are multidimensional and they are represented by multidimensional partial differential equations. So, the differential operators that we have to deal with are going to be multidimensional. So, we do need multidimensional approximations, multidimensional difference approximations to multidimensional differential operators, right. So, typically multidimensional difference operators are implemented on a grid, right, in a grid in 2D it is usually a rectangular grid, and in 3D it is a 3-dimensional ordered grid. So, it is like a grid rectangular parallelepiped in 3D, the grid is like a rectangular parallelepiped in 3D. A typical grid in 2D would be a rectangular grid in the x and y plane with grid spacings hx and hy in the x and y directions. My grid spacing need not be the same in the x and y directions. I can have different grid in the x direction and different grid in the y direction, and this gives rise to points xi is equal to x0 plus ihx, yj is equal to y0 plus jhy, right. So, ith term from the ith location on the grid, the ith location on the grid is given by x0 plus I times hx, where hx is the grid size in the x direction, while the jth location in the y direction is given by y0 plus j times hy. The central difference approximations to the partial derivatives in x and y, del ux and del uy, can then be given by del x is equal to ui plus 1 j minus ui minus 1 j by 2 hx. Now, note several things. This involves only I am taking in the x direction, right. So, I plus 1, I minus 1, the jth index remains fixed, right, and similarly when we look at del u del y, we have u I j plus 1 minus u I j minus 1 by twice h y plus of course the error terms, right. Now, we have used, it is obvious that we have used the central difference operator, but note that we have used it with a step size that is twice the actual step size, the step size that we talked about, right. So, we have used twice that, which is perfectly fine, right, there is no problem with that, right. We have used this with twice the step size for the central difference operator, because when we define the central difference operator, we said that that is equal to u I plus half minus u I minus half. So, at a grid point I am taking half a step on the left, half a step to the right, right. But instead of here I am taking a full step to the left, full step to the right, that is perfectly fine if I divide by 2 h x, right, if I divide by 2 h x. Also, let us recall we have looked at this expression before, right, the relationship between the kth order derivative, the kth order differential operator and the kth order central difference operator, right. We looked at this relationship before, we found that it was like this, right. Hence, del u del x, so from here we can directly get the order of the error, right. So, del u del x is equal to 1 by 2 h times del u, right, 1 by 2 h times del u plus order h square plus a term of order, because if we put k is equal to 1, right, k is equal to 1, that is telling me that the derivative is equal to h to the power minus 1, right, h to the power minus 1. So, there is 1 by h, right, del u, right, again 1 plus order h square plus the term is of order h square, right. Is that clear? We have this 2 again because of the, we have taken twice the step, right. So, it is clear that in this expression, therefore, in this expression the error terms are of order h square, right, the error terms are of order h square. So, this is second order accurate, right, this is second order accurate. If the forward difference operator is used to approximate the derivative, then we have del u del x is equal to u I plus 1 j minus u I j, right. The forward difference, you go forward, right, and subtract, right. So, u I plus 1 j minus u I j by h plus error terms. Again these error terms are going to be linear, right, they are going to be of order h, right. So, in this case the difference approximation becomes unsymmetric, you can see it is unsymmetric, right. If we are looking at something at I, right, and then it is unsymmetric about I, right. So, I plus 1 minus I, since it becomes, so that is why it becomes unsymmetric. In addition, the error is of first order, not second order in the step size, not second order in the step size like here, it is first order in the step size, as is always true in case of the central difference operator. The reason, again let us go back, the reason for the reduction in accuracy, we have talked about this earlier, just to recapitulate, is of course due to the relation between the forward difference operator and the derivative. Unlike this relation between the central difference operator and the derivative, which involves this h square term, in case of the forward difference operator, that was given by this, right, and xi del to the power k f x was equal to h to the power k f k xi, right, and we said that xi belongs to x plus k h, right. So, xi will become closer and closer to x as, and it is dependent on h, right. So, as h becomes smaller, xi is going to be closer and closer to h, but that relation is linear, right, that relation is linear, right. Since xi goes to x linearly with step size h, as you reduce h, xi becomes closer to x, but it becomes closer to x, that relation it decreases linearly with h. As h decreases, that relation xi becomes closer to x in a linear fashion, right, while in the other case as h reduce it, as h became smaller, the error became smaller like h square, right. So, in one case if the error was 0.1, in the next if I reduced h, it would become 0.01, right, it would become 0.01, right, it would go as h square, right, if my h is of order, right. Is that clear? Is h is of order 0.1, then the error is of order 0.01, right, and similarly if it is 0.01, it would be 0.0001, right. So, it goes, it becomes, so if I increase the order by 1/10, that is reduced by square of that, right. So, the error too reduces linearly with step size in this case, right. So, therefore, this is of order h, the error is of order h, right. So, if we are so that is something very important. Again, we recognize that depending on our choice of the difference operator, we can encounter different error terms, right. So, typically in most numerical algorithms, particularly most commercial codes, they will insist on difference operators or integration algorithms which are at least second order accurate, right, which are at least second order accurate. If we are solving second order partial differential equations, we have to deal with second order partial. So, we have just looked at first order partial partial derivatives of order 1, right, but when you look at second order partial differential equations, you have to look at second order partial derivatives. For instance, we looked at the wave equation, we looked at our diffusion equation, we looked at our elliptic equation, Laplace's equation. In all those equations, we encountered the Laplacian, that was common, right, the Laplacian was present everywhere, right. So, in order to solve those equations, we have to be able to represent, we have to write a difference equation for the Laplacian on a grid, right. So, we have to represent the Laplacian operator in terms of difference operations either in 2D or in 3D space. How do we do that? The simplest approximation to the Laplacian is the 5-point operator. It is called a 5-point operator because we will come to that, why it is called a 5-point operator. But this is the Laplacian, this is an approximation to the Laplacian in one direction, this is the approximation to the Laplacian in the other direction, right. So, you can see it involves ui plus 1j minus uij ui minus 1j divided by h square, right. Now, there is h square, you see can see that instead of h, because this is a second order difference operator, right. And similarly, this is the so you can, if you think of I as representing the index in the x direction. So, the first part of this, the first part is representing del square u del x square, right, the first term. The second term represents del square u del y square, right. So, that is the simplest approximation to the Laplacian. Again, it is called a 5-point operator because you can see it involves the evaluation of the function at 5 points, at I plus 1, I minus 1, j plus 1, j minus 1, and of course, at I j itself, right. So, it involves evaluating the function at 5 points, that is why it is called the 5-point operator. And it is also clear that we have used the second order central difference operator in this case, since del square f a is equal to f a plus h minus twice f a plus f a minus h. We have seen that earlier on, right. We showed that maybe in the first lecture on differential operators, right, that del square f a is equal to f a plus h minus twice f a plus f a minus h. You can see that we have used that here, because if you can u I plus 1 is actually one step forward. So, that corresponds to plus h, right. U I j is of course the function evaluated at the point that we want to evaluate the Laplacian, right. So, that is f a, that corresponds to f a, and a minus h, that corresponds to u I minus 1, right, that corresponds to u I minus 1. So, this is very similar to that, right, you can see that, right. and again this is just the same thing except that this is in the y direction, that is in the y direction. Also let us recall from our previous relationship that we just saw here, right, f square a means the differential of f double derivative of f, right, that can be written as h minus square central the central difference operator applied twice plus the error term which is of order h square, right. Thus, the error of the order of the error in the 5-point operator approximating the Laplacian is of order h square, right, is of order h square, and therefore, we can write del 2 5 uij is equal to the Laplacian operator plus this error term, and it can be shown that this error term is of this form. You can see by comparing with this, right, you have f to the power 4, right, which basically involves the fourth derivative of my u, of my function u, right. So, the error is something, some constant times h square times the fourth in terms involving the fourth derivative of u, right. So, this by approximating the Laplacian with this 5-point difference operator, we are going to get an error with like this, which is of order h square. As you reduce the size, as you change the mesh size h, the error is going to reduce as h square, right. It is going to reduce by h square, right. So, and it is, and its magnitude is given by the actually the magnitude of my fourth derivative of my function, right, which you can expect to be small, right. As you take higher and higher derivatives, you expect those derivatives to become smaller for a well behaved function, right, for a well behaved function. So, this operator is this 5-point difference operator is sometimes represented graphically as shown in the figure, right, where the terms in those little circles represent the coefficients of the function values in the coefficients of the function values in the difference formula, right. So, the function values had 1 minus 2, right. So, 1 minus 2 1 in one direction, again 1 minus 2 1 in the other direction. So, at the center it becomes minus 4, right, and 1 1 1 1. So, that is represented like this, right, that is sometimes represented like this. Now, it turns out that there is another approximation to the Laplacian operator, not just this 5-point operator, and this involves evaluating the function values at diagonal locations of the grid. So, here we evaluated the function values at the original location, the point at which we want to find the Laplacian, plus h in the x direction minus h in the x direction, plus h in the y direction minus h in the y direction. Instead of this, we can evaluate the function values at the diagonal points on the grid, right, and this cross del square cross uij, cross meaning the diagonal Laplacian operator, it involves evaluating the function value at I plus 1 j plus 1, which if we look at the previous picture, that is basically evaluating the function value here I minus 1 j minus 1, which involves evaluating the function value here, right, I minus 1 j minus 1, then I plus 1 j minus 1, which probably involves evaluating the function value I plus 1 j minus 1, which involves evaluating the function value here, and I minus 1 j plus 1, which involves evaluating the function value here, right. So, it involves the diagonal terms on the grid, right, diagonal terms on the grid plus the function value at the location where we want to evaluate the Laplacian, right, that by h square. So, this is another approximation to the Laplacian, right, and sometimes we put the two together. We use the 5-point operation as well as the diagonal approximation and combine them with some scale them with some coefficients and then add them together, making sure that the sum of the coefficients adds up to 1, right. So we are combining these two operators, sort of weighing them, right, weighing the 5-point operator by a certain coefficient, weighing the diagonal operator by a certain coefficient, making sure that the sum of the weights is 1, and saying that that is a representation of my actual Laplacian, right. That is a representation of my. So, in this case, for instance, we can scale it by 2/3 and 1/3. We scale the 5-point difference operator by 2/3, the diagonal difference operator by 1/3, right. And similarly, for more complicated differential expressions, it is possible to construct difference operators in similar fashion by combining more than one difference operator, right, by combining more than one difference operator. So, this is an example of that, where we have combined the 5-point, right, with the cross difference operator to get what is called a 9-point Laplacian, and this is probably the most commonly used representation of the Laplacian. Neither this nor this is commonly used, this is what is most commonly used, the 9-point representation of the Laplacian, right. So, here I have said 6 times h square this plus is equal to 6 times that is equal to 4 times this plus 2 times that, right. So, 4 times this plus 2 times that. Actually, this is actually representing, I should probably have mentioned that there is a 2 here, right. So, this is actually a representation of 2 del square x u I j, right. This is 2 del square u x I j is given by that by h square, right. So, that is fine. So, that involves terms like this, that involves terms like that, and then 4 times that, if we add that, we get something like this, right. So, this is 6 h square del square by 9. So, if I divide this, if I scale all the coefficients by these appropriate values, right, the term here is scaled by 4, the term here is scaled by 1, this term I scaled by minus 20, right, and I add it all together and I divide it by 6, I am going to get my representation of my 9-point Laplacian operator. All this 6 and 4, this is just to get coefficients which are, instead of fractions, we have whole numbers, so that the coefficients are whole numbers, right. So, that to make sure that my coefficients are whole numbers rather than fractions, because fractions, as soon as you have fractions, you have to take division, right. As soon as you take division, you introduce errors, right. You introduce errors, round off errors. So, that is why we prefer to deal with whole numbers as our coefficients, right. Instead of having some fraction scaling the function value, we want to scale it with a whole number. So, at least there we do not introduce any round off errors, right. And then we have to, if we have to evaluate the Laplacian, we have to divide it by 6, but at least we are doing the division only once, right. After doing all these multiplications with these whole numbers, we are doing the division only once, while if we used fractions for each coefficient, we would use we would introduce round off errors every time we add to that difference formula, right. So, every term in my difference formula would have a round off error, while if I scale with 4, 1 and like that minus 20, I would have round off error only when I divide the whole thing by 6, right. That is the idea. This formula is useful in many situations because its remainder term, again this remainder term is a second order term, right, that is always going to be true. But in this case, the remainder term is actually del 4, right, which is basically del square, right. So, that's a nice form, right, it involves the square of, so it is like this. So, your Laplacian, this is your true Laplacian, this is your numerical representation of the Laplacian, and the error is of the order of the square of the Laplacian. That is why this is sort of nice, right, because it gives it, the error is of the square of the order of the square of the Laplacian. Okay, so that was okay. So so in a rectangular domain, everything is fine, right? You have a regular grid point, it's you can know where to evaluate the, you know your difference operators. It's very nice. But in most real world problems you do not have rectangular domains. Why don't you have rectangular domains? Well, because of two reasons. One reason is mostly because your geometry is non-rectangular, right? You rarely have a rectangular geometry. You may have an arbitrary geometry, and it's very hard to divide it into rectangles, right? It's very easy to divide it into triangles, but it's very hard to divide it into rectangles, right? So you're almost never going to have, unless it's a made up problem or it's a very simple problem, you're never going to have a rectangular grid, right? But any real domain, it is almost always possible to divide it into a rectangular grid, and then the part which where I cannot have a rectangular grid, I can divide it into a triangle. I can have a triangular grid there, right? So it is very important that we be able to approximate our differential operators on a triangular grid, right? And also the triangular grid can approximate the geometry on the boundary, particularly if an irregular triangular grid is allowed, right. So, regular triangular grid, again it is restrictive, right, but if I have a free grid, right, I can put points wherever I like. I do not have to put points in a particular fashion, plus h, minus h. I do not have to put points like that. If I put points arbitrarily, then it is much more easy for me to approximate the geometry, right. It is much more easy for me to approximate the geometry. And another reason why while a free triangular grid is particularly useful, because consider a real world problem where I have regions of sharp gradients, right, where my solution variable, my u, is not the same everywhere. Is not, I don't mean to say not the same everywhere, but it doesn't have, it varies differently at different locations, where at some regions you have a sharp gradient in u, and in other regions u is more or less relatively flat, right. It varies very slowly. In other regions it varies very fast, right. So, in the region where u varies very fast, where my function value of interest varies very fast, I would like to have more grid points there, right, because I know that that function value is high, that function is varying in a highly nonlinear fashion. So, unless I have sufficient number of grid points in that location, I would not be able to capture that highly nonlinear variation. So, it is so with a regular grid point, it is very hard to capture all these things, right, that nonlinear regions of sharp gradient. For instance, in solid mechanics, one thinks of stress concentrations, right. You have a hole and the stress concentration around that hole, right. So, you know that if you have to capture that, you must have lots of grid points near the edge of the hole, right, while far away from the hole, where the variable of interest, for instance the displacement, is varying relatively smoothly, you need not have that many grid points, right. So, and if we have to be able to write these difference operators on, first of all, on a triangular mesh, number 2 on an irregular mesh, right, an irregular grid. Because of this, a complicated plane region is better approximated by a grid of triangles. It is also relatively easy to adopt the density of grid points to the behavior of the function. What do I mean by that? Well, I mean exactly what I just said, that when you have a sharp gradient, you can introduce more grid points right there. For example, right, so I just mentioned that, right, to get a sharper resolution of the solution. But the difference formula we have encountered so far assume a uniformly spaced grid. How do these difference formula change if this grid is irregular, right? What will be the difference formula if the grid is irregular? In particular, since the Laplacian is the most interesting, is the most important difference formula for second order partial differential equations, what is the difference formula for a Laplacian on a triangular grid? What is it on a regular triangular grid? And what is it on an irregular triangular grid? So, we will first obtain a difference expression for the Laplacian over a regular triangular mesh. We will then extend those ideas to an irregular triangular grid. So, I have used the word mesh and grid interchangeably, right, although they might have certain but in this case we mean the same thing, right. So, let us consider the triangular grid shown in this picture, right, where I have a grid of triangles, and suppose I want to evaluate my function value at x, right. I want to evaluate my function value at x, calculate, and I am interested in not only the values in the I am actually interested in evaluating the Laplacian at x, right. I am and x is located inside a particular triangle, right, and the grid points I am denoting as 1, 2 and 3. Now, in this case I have a regular triangular grid. So, my size is h, right, all my triangles have size h, and I say that I assume that this is my origin, this is the origin, right. So, we define the linear interpolant of u as a function I u of x, where I u of x is equal to u x at the grid points 1, 2, 3 to n, right, and is a linear function of the grid point values u x 1, u x 2, u x n inside the triangles, right. So, in order to get an expression for the Laplacian, first I have to define an interpolant, right, an interpolant which tells me what is the value of u at x if I know the values of u at these grid point locations at 1, 2 and 3. If I know the values of u at 1, 2 and 3, I can use my interpolant to find the value of u at x. And it is, of course, we assume that u possesses sufficiently strong continuity properties which will allow us to evaluate all, so that all these derivatives that we, for instance, for us the second order partial derivatives exist, right. So, using barycentric coordinates, basically triangular coordinates, like you might be familiar with them with that name, the coordinates of the point x can be found in terms of the coordinates of the grid points located at the vertices of the triangle in which x lies, right. So, I can find out the coordinates of this point x in terms of the coordinates of these points 1, 2 and 3 by interpolating the coordinates, and I am saying that those interpolant I am going to use, they are called theta 1, theta 2 and theta 3, right. Theta 1 times the coordinate at this location, theta 1 times the coordinate at this location, plus theta 2 times the coordinate at this location, plus theta 3 times the coordinate at this location is going to give me the coordinate of x. And the condition is that theta 1 plus theta 2 plus theta 3 is equal to 1, right, and theta 1, theta 2, theta 3 are all positive, right. So, these are my barycentric coordinates, right, theta 1, theta 2 and theta 3 are the barycentric coordinates of the point x, right. So, the value of the interpolant I u x is then calculated from the function values at the vertex in similar manner, right. So, I basically say I u x y at, basically I am saying that if I want to evaluate u at x y, x has got two parts, right, two components x and y, right. So, if I want to evaluate u at x y, I am going to do that by taking theta 1 times u 1, u at 1 which is u at 0 0 plus theta 2 at u at 2 which is equal to, if this is 0 0, if this is 0 0, that must be minus h 0, and this at 3, this must be 0 h, right, this must be 0 h. So, I am evaluating u at x y by theta 1 u 0 0 plus theta 2 u at minus h 0 plus theta 3 u at h at 0 h, right. So, this is how I am going to evaluate my interpolants, and taking advantage of the regularity of the grid, we can write analogously I u x plus h y. So, u at x y is given by that, right, u at x y is given by that. So, now I am interested in evaluating u at x plus h y. Where would x plus h y be? X plus h y would be exactly in this triangle, right. It would be x plus h in the x direction, right. So, x, so here it is x y, the coordinates, the Cartesian coordinates of that point are small x and small y. So, if I am looking at if I am looking for a point with Cartesian coordinates small x plus h y, that would be somewhere in that triangle, right, just h from this point along the x direction, right. But what do you notice about that point? That point lies in this triangle. So, the barycentric coordinates of that point have to be theta 1, theta 2 and theta 3 because of the regularity of the grid. If I am looking at this point, that point has barycentric coordinates theta 1, theta 2, theta 3. If I am looking at the mirror image of that point in this triangle, which is x plus h y, then the barycentric coordinates of that point right here are again going to be theta 1, theta 2 and theta 3. But now it will involve the, now let us go back and take a look. So, since so because of the regularity of the grid, we can write I u x plus h y is equal to theta 1 u h 0. Earlier on it was u at 0 0, right, u at 0 0. Now we are evaluating u at h 0, right, because everything has shifted by h in the x direction, right. So, u at h 0, u at h 0 plus theta 2 u at 0 0. See, so that involves this point theta 2 u at 0 0 and theta 3 at this point, which is actually h h, right, which is at h h. So, theta 3 u at h h, but you can see because of the regularity of the grid we can still use theta 1, theta 2, theta 3, because the barycentric coordinates have not changed, right, of that new point are the same as for the old point, right. Similarly, I u x minus h y, this means I have to shift one h to the left, right. So, I am going to move to this triangle, I am going to move to this triangle, right, and x would be somewhere here, right. So, x would be somewhere here, and that would involve theta 1 u minus h 0, theta 2 u minus 2 h 0, theta 3 u minus h minus h. So, if I write it in terms of indices, I have u I minus 1 j, right. This is u I minus 2 j, because I have moved negative 2 in the x direction, but I have not moved in the y direction. So, that remains j, right, and here it is I have moved I 1 in the x direction and 1 in the y direction. So, I have u I minus 1 j minus 1, right. Similarly, I can write r u x y plus h like this using the same sort of argument. Now, in this case I am looking at a point right here, right, I am looking at a point right here, right, I am looking at a point right here, and then I y minus h where I am looking at a point in this triangle, right. So, in that case I get something like that. So, I can write these r u x plus h y, r u x minus h y, r u x y plus h and r u x y minus h in terms of these grid point values scaled by my barycentric coordinates, but you note that we are using the barycentric coordinates of my original point x, right. I am using the barycentric coordinates of the point x at which I want to evaluate the Laplacian, right. I do not have to recalculate the barycentric coordinates because of the regularity of the grid, right. So, now what do I get? So, again let us go back to our definition of the 5-point difference operator, which was del 2 5 u I j is equal to u I plus 1 j, u I j, u I minus 1 j, and so on and so forth. So, now I am saying that del 2 5 I u I j is equal to I u I plus 1 j minus 2 I u I j plus I u I minus 1 j plus this, right. So, I have introduced this I, right, because I am going to now evaluate the Laplacian on the interpolant, right, on the interpolant, right. So, hence I can say that del 2 5 I u I u x is equal to I u I plus 1 j, I can write as I u x plus h y, right. X index changes by 1, y index remains the same, minus 2 I u x y plus I u x minus h y there, and here I have I u I j plus 1. So, I u x y plus h minus 2 I u x y plus I u x y minus h by x square h square, right. And then I substitute my previously evaluated expressions for I u x plus h y, I u x minus h y, I u x y plus h, I u x y minus h in this expression, right. And therefore, I get as an expression like this involving u y plus 1 j, u I j, and so on and so forth, right. I get something like this. And then what do I do? Well, I decide to pull out all terms with theta 1. I pull out all terms with theta 2 together, and I pull out all terms with theta 3 together. Then what do I get? Then I get something like this: theta 1 plus h square times this, theta 2 by h square times that, theta 3 by h square times this, right. And what are these? That this term within curly brackets here is nothing but theta 1 times del 2 5 u I j, right, del 2 5 u I j. You can see u I plus 1 j minus 2 u I j plus u I minus 1 j plus u I j plus 1 minus 2 u I j plus u I j minus 1. So, we have seen that is equal to del 2 5 j. What about that term? Well, that is nothing but del 2 5 u I minus 1 j, because this is I. So, you replace here I by I minus 1, right, and you will get that, right. So, if I replace I by I minus 1 here, I am going to get this. So, right. So, I by I minus 1, I by I minus 1, I get I minus 2, j does not change, right. I so only, right. So, I get that, right. I replace by I minus 1, I by I minus 1, so that is that. So, that is nothing but my Laplacian evaluated at u minus 1 j, and if you look at this, this is nothing but u I j plus 1, where I have replaced this j by j plus 1, right. So, what do I get? So, I get del 2 5 I u x, the Laplacian evaluated at x is equal to theta 1 times the Laplacian evaluated at I j plus theta 2 times the Laplacian evaluated at I minus 1 j plus theta 3 times the Laplacian evaluated at I, that is a mistake, I j plus 1, right. That is the Laplacian evaluated at I j plus 1. But what is I j, I minus 1 j and I j? These indices represent the points on that triangle, right. They just represent these points. They just represent these points, right, this point, that point, and that point, right. So, finally, what do I get? Finally, I get that my Laplacian evaluated at an integral at an internal point is equal to the Laplacian evaluated at my grid points scaled by my barycentric operator of the point at which I want to evaluate the Laplacian, right, scaled by the barycentric point of the barycentric coordinates of the point at which I want to evaluate the Laplacian. Thus, the Laplacian at an arbitrary point x located within a triangle is the weighted sum of the Laplacians calculated at the 3 vertices of the triangle, the weights being the barycentric coordinates of the point x in the triangle. So, next I want to consider an irregular grid. I want to evaluate the Laplacian on an irregular grid, and I want to show you how to do that. I will do it for a simple case, because for a complicated case it is hard to explain, but once you understand it for a simple case, it is possible to extend it for complicated cases as well. But since we are out of time, we have to do that next lecture. Thank you.